welcome everyone to our last robotics seminar of the semester. So it's my pleasure to introduce Jeannette Bohg for the seminar today. So Jeannette is an assistant professor at Stanford in the computer science department. She received her PhD at KTH in Stockholm before moving to the Max Planck Institute as a group leader and then moving to Stanford as faculty in 2017. So Jeannette's work is kind of broadly in the area of robot perception and robot learning for manipulation. She has a whole kind of body of really exciting work in this area. She's worked on techniques for self-supervised learning, for learning good representations, for vision, for doing visual motor control, manipulation. She's worked on active perception, interactive perception. And I guess most recently, she and her collaborators have been kind of leading the charge in terms of scaling up robot learning. And we're going to hear some piece of that story today, and I guess some of the challenges as well associated with just scaling things up. She's received a number of awards for her work, including Early Career Award from the Robotics and Automation Society, Early Career Award from RSS, Best Paper Award at ICRA, and also from RAL, and many others as well. So Jeannette, thanks so much for taking the time to visit us. We're looking forward to that.
Thank you so much for the nice introduction. Thank you for the invitation. Yeah, it's my first time at Princeton, so I'm really looking forward to seeing everything, meeting everyone, yeah, seeing maybe the Einstein monument later. I was going to look at that one. So today I wanted to talk about cross-embodiment learning in robotics, and what I mean by this is that it would be great if we could have robots that learn from other embodiments, meaning like either other robots or even people demonstrating something to them. And before I go into how to do that in a bit, I wanted to first take a little step back and actually motivate why that is actually an interesting problem, or why we would even want to do that, because it's not like, it's still challenging to actually do that. First, in this process of taking a step back, I want to explain a little bit what a foundation model is, if in case people haven't heard of it yet. I guess like everyone has used ChatGPT, so I feel like people know what a foundation model is, but just in case, I wanted to actually bring up the official, maybe, I don't know, the official maybe definition as was suggested in this paper. That is, a foundation model is a large model that is trained on vast quantities of data, often through self-supervision, therefore not needing labels, such that it can be adapted to a wide range of downstream tasks. And so basically it's a model that gives some input, produces some output, and in the most simple terms. And I guess the kind of famous or very well-known models in that realm are not actually robotics models, but more like models in NLP, like ChatGPT or things like DALL-E, where you provide a prompt and then it generates an image that matches that prompt, or image captioning and visual question answering things, or also more recently, more vision-based models like segment anything and stuff like this. And what is so interesting about these models is that they can actually zero-shot generalize to some of the tasks that they were not specifically trained on, which is kind of very astounding and cool. And what turns out is possible that these foundation models from other areas can actually be plugged into a robotics system to enable generalization, and I feel like they often like open doors into new problems that we can suddenly solve because of these outside models. And so examples are like suddenly vision kind of works, which wasn't the case for a long time, I think, in robotics. When you took works on the computer vision community that were supposed to be state of the art, they actually not really worked in the expected way on a robotic system. But now there are models like, for example, segment anything that actually are really useful. Of course, ChatGPT or GPT-4 turns out to be really useful. CLIP is often used in robotics as well to provide all the semantic understanding, or in the case of GPT-4, like even reasoning, high-level reasoning about plans, or you can, given a user prompt, actually imagine what you would want to see in the scene using systems like DALL-E. Or you can use open vocabulary models to actually detect objects like this one. So these are just like a few examples of outside foundation models or foundation models that are outside of the world of robotics that actually turn out to be really useful in robotics as well when plugged into a larger system. But I think one thing that we have to acknowledge is that the actual maybe core of robotics, which is sensory motor capabilities like manipulation, are far inferior to human capabilities. And let me just take this example from colleagues and friends from Google. That is the paper of RT2 that has made a big splash that shows, and I'm showing here an example where this robot is tasked to pick up an extinct animal, and it does that in this way. And it figures out like, oh, of all the toys that I see on this table, the extinct animal is this dinosaur that it visually actually observed. And I think that made everyone just like, explode their brains, especially if you're not in robotics maybe, because it's like a cool reasoning ability, right? Like to just see an image and do this inference of like, oh, it must be the dinosaur, it is the extinct animal, without actually having like somehow hard-coded this, but just using this capability of this model that was trained on vision and language data without collecting any, robot data. But what I also want to point out is that that's a really cool ability. But what I also find here is that this grasping is kind of very simple, right? Like even a toddler could probably do this more swift. This is also like sped up 10 times, which is not actually said in this video, right? But it's like in terms of sensory motor capabilities, this is pretty not so interesting. And so if we look at actual human capabilities of manipulation, such as this expert taking apart an iPhone and trying to repair it, I mean, we are far away from this, right? Like of using tools and prying objects, like tiny objects, and using this screwdriver on these tiny screws and all of this. I mean, we're far away from this one doing this actually with robots. And even I would claim that we're far away from doing any kind of everyday human manipulation tasks such as these ones, especially when it comes to just deploying a robot into a new apartment, right? Like it might work if you do it exactly in that lab where you've collected the demonstrations, for example, right? But it doesn't work in any environment. So we're really far away from this. And I think one quest that a lot of people are after right now is to find this robotics foundation model. So a model that can actually do the same thing that ChatGPT can do for NLP, do in robotics actually, and especially for these sensory motor capabilities. And what would we want this model to do? We would want to have it generalize over all these different objects, all these different environments, all these different embodiments, which is actually going to be the core of this talk, and all of these different tasks as well. And so now, before I go more into this embodiment part, let's just quickly clarify actually what we would need a robot to do, and therefore what a robotics foundation model actually would need to be. So let's look at this robot that tries to grasp this drill that is up there on the right. And what would it need to do? It basically needs to perceive through its sensors, so maybe its cameras or also its touch sensors, the environment, then process this in some way and provide this as input to a policy or to a controller. And that policy outputs actions. And this could be, for example, let's say motor torques, right, that it sends to this robot in some way. And then the robot moves when it executes these actions, and immediately the whatever it perceived before, right, is going to change, and therefore it has to perceive again, feed this into the policy, and so on. So, and this loops runs in a millisecond scale. Okay, so what would be a robotics foundation model? It would be some component that basically defines this policy, right? Like to actually output these actions and hopefully enables us to do this sensory motor control in a more generalizable way than whatever we have right now. So again, what would this robotics foundation model be? It could be a dynamics model, for example, right? That takes as input an action and past observation and then predicts future observations. It could be a policy that takes in observations and maybe a goal and outputs actions directly. or it could also be some inverse reinforcement, like a reward model, basically, that takes in observations and actions and infers what the reward function is, right? So all of these are examples of what a robotics foundation model that a lot of people are looking for right now could be. And so one thing that is really different here from the NLP and computer vision type foundation models is that there's a dependency on actions. And that is what makes getting the data that is available in NLP and in computer vision so hard to get in robotics, right? This dependency. Because what it means is that the data that you have to collect has to have that label or that information somehow in there. Is there a question? You look like no. Yeah, also feel free to ask any questions in between, of course. So I would claim one of the biggest bottlenecks, I don't think it's the only one, but one of the biggest bottlenecks in robot learning is the lack of data. And just to give you an idea of what the scale of this lag actually is I made a little simple bar plot here, actually inspired by what one of my students done, which I thought was like really great, to simplify it down to this. So what you see here is how many trillions of tokens some foundation models had now a few months ago, right? So already this is exceeded. I don't have the current numbers, but this is from a few months ago. So you have 3.6 trillion tokens or 2 trillion tokens, meaning words, in the data set that these models have been trained on. And now here we have robotics, like the biggest data sets in robotics. 130K episodes in the RT1 data set, which is mostly collected on a shelf unit, by the way, or 70K episodes from this droid data set that is multi-institutional or cross-institutional, which has been collected recently. And so you see that this is like an astounding difference in data. And if you wanted to bring up robotics to the same level of data that you have in NLP or computer vision, you would need to scale up the current data collection techniques by 27 million, okay? So that's definitely not possible on real hardware. Yes?
Well, a quick question just here is, can you speak a little about the difference between tokens and episodes?
Oh, yeah.
Episodes.
Yeah, that's a very good point, right? Like I'm just making this little back of the envelope computation here, assuming that the data, an episode is the same as a word, but of course an episode is really literally doing like one task, like picking up this water bottle or opening this lid or something like this. So this is like a whole time extended series of states and actions basically that you collect. So it's actually already much more data, but I would also, so it's, this is just an approximation to give you an idea. But also, in NLP, you just need to predict words. In robotics, you actually need to predict continuous valued information on all of this, right? Like, so whether you actually just need 3.6 million to go the same way as NLP is going is also a question, right? But yeah, this is just like to give you a rough idea. Any other questions about this? Yeah?
Does it need to be like current time steps of joint control? Can it be like surrogates like closes of the dependent factor, etc.?
Sure. Yeah. That's what a lot of people do. Actually, in this data set.
Need as much as data if we change the control space.
Yeah. So I completely agree. You have to be smart. You have to be smart about picking that action space that the policy outputs. And actually, most of these data sets, both of these data sets, they do have the joint angles in there, but when they learn the policies, they learn it on the end effector, in the end effector space. Yeah. They learn to output the end effector space.
Oh, but I was actually wondering if we were kind of used, like, if we want to improve the free space, we can use motion planning. So all we need is data, like operation space control. We can actually command with target pose, which is far away from the pose.
Yeah.
That will probably like reduce the number of.
Sure, but that's what they have to use, right? Like so that's what used under the hood, right? So they have a policy on the high level that runs at a terrible control rate, which is like once per second if you use RT2 because it's running actually in the cloud, or at 20 hertz that outputs a goal pose, basically a waypoint, you can think of it, of the end effector pose. And then you need an operational space controller or some other controller that actually brings the arm with all its joint, right, like in that into that post to actually reach it. Yeah, does that explain or answer your question? Yeah, okay. So that's already a prior that is embedded here, right, that nobody talks about. But yes?
Are these episodes all open source episodes?
Yes, they actually are.
Okay. So are there even more that are just kind of like closed off, not available for?
No, actually the ones I'm mentioning here,
Yeah.
these you can actually download
Okay.
if you want. Yeah, these are open source. Okay, so so again, I would claim scaling up what we do right now to get real robot data is not really the way to go. But we try anyway because it's good to have more data. That's kind of like, I think that's maybe not really debatable. So having more data is good. I just don't think we can get all the way with just collecting data. But here's this example from this Droid dataset that we recently published. So this is like a cross-institutional data collection effort where we basically replicated one platform to collect data across all of these 13 institutions and like even more labs. And this was just released open source, and it has like RGB data, but also depth data in there, or stereo cameras, multiple. And this is actually, again, like just to visualize why scaling this up by 27 million is not really a thing we want to do. So this is Jimmy Wu, Princeton graduate student visiting Stanford. This is what he does at Stanford. Oh no, he actually does way more. He's like the person behind TidyBot. If you've seen that, I'm not going to talk about this work today. But he was also really interested in this large-scale project, right, like cross-institutional. And he filmed himself actually doing the teleoperation of here, emptying his dishwasher at home and like doing all of these tasks. And like every student it's mostly students who took this platform actually home to their home, they spent 40 hours doing this. Okay, so 40 hours, and they really burn out on this. So that's again like why we can't scale this up by 27 million. But
Hey, just one question I'm curious about.
Yeah.
He looks so tense, and it looks. I'm struck by how much more difficult it looks to teleoperate than for a human to just walk over it and do it.
I agree.
There's no haptic device.
And there is no haptic device. Yeah, he has like this Oculus controller in the hand, right? Like there's no feedback on contact or whatever. This is a compliant arm, so you are a little bit more safe, like right, like when you make contact with the environment. But yeah, I mean, Jimmy is actually a very concerned person when it comes to robot hardware. So I think that's why he looks so tense, right? Like he doesn't want to break the robot because that's gonna jeopardize the whole effort. But yeah, I mean, again, like that's also what's happening, right? Like the hardware breaks all the time. More questions on this? Yeah, okay, cool. So, collecting data, it's a pain. But we do it anyway because if we have more data, it will certainly help. It's maybe not the only answer, right? But let's go that direction for today, and I'm happy to talk more about more directions, like why we are all meeting today. But here is this typical robot imitation learning pipeline that you've already seen just with a different arm, a different student. This is Pete Florence actually when he was at MIT, and it's basically a grad student, right, like teleoperating this robot in the specific environment that the task will also be performed in, right? And it's the same embodiment that the data was collected on and that the policy will be played out. Same observations and action pairs. And then here is a caricature of how a robot learning project typically looks like. And it's basically throttled by a grad student's motivation and frustration maybe, and availability of hardware as well, right? Where all the data collection, which is like the most tedious part again, like happens at the very end. And so what if we can like alleviate that a little bit? And so here's an example where we can see that real intelligence, however we want to define this, right, like can actually maybe learn from demos in a completely different environment to learn the right behavior to get to whatever, the cookies or something like this, right? Oh, in this case, it must be some sausages on that stove. But you get the idea, right? Like we want robots to be able to do that as well. So we wanted to learn from a different embodiment, and potentially this different embodiment is having like a completely different strategy, right? But we still wanted to understand like what to actually do with its own body here. Okay, so this is where this idea came about of like how to help this whole data collection effort and how to alleviate this pain a little bit. The idea is to basically pool all the robotics data that has been already collected in the world, let's say, and then try to basically generalize or basically transfer skills that have been learned on one robot to another robot as well. And so this is this project called Open X-Embodiment. And again, it was like between 21 institutions and 34 different research labs. I don't know if Princeton also maybe contributed a data set. I'm not sure, but it keeps growing actually. So it's not anymore only 60 data sets. And Droid, for example, is also now part of it. It came out later. And so because it's such a big collaboration, these are all the people that contributed to it. And you will see some familiar names in there, I'm sure. And it's basically this new robot learning data set that is open source, again, and it has actually 1 million episodes. So still that factor, right, like this, you know, I don't know by how much, I mean, we know by how much it diminished, but it's still only 1 million trajectories, but still, that's a lot of data. But of course, the challenge is now, how do you actually transfer between these different embodiments? So here's some samples from this data set of some of these 60 data sets that are actually pooled together. You see there are many different viewpoints, many different embodiments, somewhat many different tasks, right? There's also some mobile robots versus only stationary robots. And here's some statistics of this data set. Again, 60 robot data sets from 34 different research labs. And you see the number of different robots there on the right, for example. So the X-arm is the one that is in the bridge data set, if some of you are familiar with that. It's like a small arm that basically did things in a toy kitchen. But you also see there are actually a lot of Franca arms that have been used in research as well with like more varied scenes. Here you have all the different skills. You see there's a lot of picking and moving things around and not so much wiping or stuff like this. And yeah, I think, and here's like an automatically generated summary of kind of the objects that were used with some summary of those categories. Okay, so that's the data set. And here is a first set of models that is learned from this data. And again, this was actually spearheaded by people in Google who led this effort. And you know, they have access to this RT1 and RT2 model. And so that's what they basically tried as the first model architecture here to learn a policy that takes as input RGB images, maybe a sequence of them, plus a language instruction, and then process it through these two different types of policy architecture. I'm not going to go in detail into this. And then outputs a discrete set of actions that are then, depending on what embodiment this policy is actually executed on, is translated into delta poses, well, actually depending on the robot, it could be delta poses, could be velocities, whether the gripper is open or closed. And some robots, they don't do rotation for some reason, I don't know. But in this case, for example, this is not what's being output by this policy. So depending on the embodiment where this policy is executed, basically this output is also transformed in different ways. Does that make sense? Any questions? Okay, so the questions that, so basically these architectures were trained on this data consisting of multiple embodiments. And then here are a bunch of questions that were asked in this paper. So one is, can I pre-train a base policy on this data of all these different robots? and then improve a performance on a new task that wasn't actually in the data set at all. And maybe this new task comes with a few demonstrations, right? Like a much smaller data set that's very specific to this demonstration. They wanted to know, okay, if I have a base policy and these few demonstrations, can I basically improve the performance over some specialized model that was initially written for these tasks? And here you see all of these different labs that were volunteering their time and effort to actually reproduce basically do this experiment with their hardware. And they had basically previously output a model and collected the data to solve all of these different tasks with some specialized architectures, okay? And so here is the result over all of these 6 different labs and 5 different tasks and 5 different labs. And so you see in the dashed bar is always the method that was originally proposed by the authors. In the middle, and the gray bar is when RT1 was basically trained on the data specific to this task. And the third bar, the rainbow one, is essentially training RT1 in conjunction with this little bit of data for this particular task. And you see that for most of them, not for all of them, this RT1X, which is basically, again, trained with all this other robot data, outperforms essentially either the specialized architectures or RT1 just being trained on this particular data. There's an outlier here, and I have no idea why this is, but I would be very interested to hear, but I didn't do the training of these models, but that is like one of my personal question marks of why this is, but I actually don't have an answer. Any questions on this? Any thoughts?
So was the experiment like 0 shot or 0?
No, it wasn't 0 shot. So for these tasks, they each came with like much smaller data on this specific task. Basically they, for generating, these numbers, the rainbow colored bars, they took this cross-embodiment data and then co-trained it with this little data that they had on this task. These ones are only trained on this data that was specifically collected for this task. Yeah. More questions? No. Okay. Okay, here's an experiment that I actually find more interesting, and I still have a lot of questions about this one as well, personally. So here, the authors wanted to know, does training on this cross-embodiment data improve performance on new unseen tasks? So specifically, the experiment that they have done, like here you can see the tasks, but the experiment they have done is they trained an RT2 model, which is this model that uses a vision language model that is only accessible to Google, on data that was directly collected on the Google robot that you've seen earlier with this extinct animal task. And that data is actually not sufficient to do very spatial tasks and do spatial reasoning, as is basically like really emphasized in these evaluation tasks here. And so for training this RT2X model, they actually mixed in basically the data from the bridge data set, which has this completely different arm that does very spatial tasks. So it has to do a lot of spatial reasoning. But again, it's like data that comes from a different robot arm, and then they tested this RT2X model on the Google robot that, if only trained with this Google data, could not do these spatial tasks. And so that's kind of a very, that I think was for me like the most astounding result, or the most interesting one, but I don't personally have, or there are still a lot of questions for me on how this actually worked, because one of the things that you see in this particular architecture is that actually the input just consists of images, and these language instructions, but there's no information about the embodiment in there. There's no information about frames. There's no information about how these objects are actually being, robots are actually controlled, like through velocity, through position deltas, absolute position. And so I'm a little confused of why this works, but maybe there were this bridge robot, this X-arm basically that's used in this bridge dataset, which is this one. Maybe it has like a very similar frame and control scheme as the Google X robot, and that's why this transfer actually worked. That's my current hypothesis. But yeah, otherwise I find this, this result actually most intriguing for me, because if that really works, and it's not just maybe overfitting or something like this, that could be really promising to learn from other embodiments. Any thoughts or more questions on this?
Just a quick clarification. So I guess the RT2X, the two data sets are the OpenX and the original RT2 data set?
Yeah, which is actually the RT1 data set, but yes. Mm-hmm. Yeah. Yeah.
Do you know if they are reasoning, or is it related to, you said you don't know, but I guess do you think that they're just training on the end effector in all cases and the motion control is separated out, so it's not going through the learning pipeline at all?
Yeah, exactly. So if you look again at this, this is why I'm confused why this works. But so you see, like, this is the data that they train on. They have like gripper open or close, position delta, or if you look up there, it has just a velocity, which is different, or there's even robots in there that only have absolute position, which is completely different. And then some of them have rotations or not. And actually to go from here to here, there has to be a specific translation mechanism that actually goes from here to this robot as well. And so they only train on these, and only have this end effector information. And actually the model has no idea if it's deltas or velocities or absolute. It just has like numbers. There's no.
It just opens the possibility that in your next slide, you add a data set that's another end effector, which is a human arm moving things around. And then maybe this would still work because you would just be looking at the end effector.
Yeah.
Just assuming it was like a gripper that was open or closed.
Yeah. So I know, like, this is definitely the promise. But, you know, I'm just questioning, like, how this actually exactly works, because probably in these 60 data sets, there's like one data set that has a left-handed coordinate system in the frame. Right? Or they have like a coordinate system where the X and the Y is completely differently rotated from the other ones. Or again, it's like a delta position versus an absolute position, which is like if you tell your robot 0, 0, 0, and it's controlled in delta positioning way, right? It's just not going to move. But if it's controlled in the absolute positioning way, it's just going to ram itself into the base, basically, which is not something you want. And so that's where I'm personally a little confused about how this exactly actually works, right? And I'm wondering if for this particular example, for these particular robots, right, it just happens to be that they have a very aligned action space, and that's why this works. But I think there's also, there's one interesting research question, and there are more in the space, is what is actually the contribution of the different data sets? What is the quality of a data set so that it can actually help you to learn skills in a better way? What kind of diversity do you need in the data? What kind of alignment do you, what kind of overlap in this action space, for example, do you need? So there are all these different questions. And I think there's also a very specific way to pick from these 60 data sets to train this model, which currently is being done by hand, right, by trial and error. And I think it would be interesting to ask, like, oh, how do you do this automatically to actually look at these data sets and understand their quality and their possibility to transfer? So yeah, I hope this is the reason why I have some questions about this, which I can't actually assess myself. Maybe Annie, you can look into this because you're a Google. Yeah, but yeah, it's an interesting question to me. Yeah, any other thoughts? Okay, cool. Yeah, so some takeaways. So I think it's an amazing new open data set that keeps growing. And the first models, I see them as a proof of concept. And I think there's a lot more you can do. Like imagine you actually align all these frames. How great could the transfer between these embodiments actually be, right? And I think there are many new and old research questions to study with this data set as well. Okay, so let me make some suggestions on what I think could be potentially done differently with these models and with this data set. So again, let's come back to this question. So the reason why this is hard is because to learn from different embodiments is because when you have a specific embodiment, you can actually do things only in a certain way, or maybe you can do something that another embodiment cannot do. And so it's really hard to understand this correspondence between these embodiments and understand how to transfer. And so that's why this is a challenging and interesting problem to investigate. And so here, I want to talk about two ideas, maybe a third one, but I don't think I'm going to get there. But on two ideas on how to learn across embodiments that are a little bit different from these initial models that we've seen and still can actually maybe use these data sets. And so the first one is a work that is actually only considering grasping. Sorry, this is the one on the left. But I think it could potentially, some ideas from there could potentially be used for actually learning from this open X-Embodiment data set as well. And here another idea is to just think about how to learn rewards that are actually specifically related to the task that has to be done and not to the embodiment, right? And doesn't try to solve actually how to basically form any correspondences between these different embodiments here, for example. Okay, so let's start with this first one, where we actually think about different hands instead of like a whole robot arm. And so one thing that maybe is already clear from the previous slide is that not only the movement of an arm, but also a good grasp depends on both the shape of the object and the geometry of the object, but also the gripper geometry, how many fingers it has, the kinematics and so on, joint limits. And in this work, we actually proposed a model that we call UniGrasp that can grasp any object, also novel object, with any gripper. That's the goal, okay? And so the way we thought about that is that we actually want to select contact points that are suitable for each of these different hands, and could also be generated on each of these different objects. And so so that's basically the main goal of this model, to then basically align these hands and the fingers. To align the fingers of the hand with these objects at these specific contact points. So in a way, those contact points we see them as a unified representation for grasping in this case. Okay, so here's an overview of how this model works. Basically, it takes as input an object point cloud and some specification of the hand that I'm going to talk about in a bit. And then we basically have this model that computes some features on these inputs and then generates these contact points on these objects. Okay, so let's talk first about this hand specification, right? Like how do we get information about the hand in there? So it's basically this model extracts gripper geometry and kinematic features and concatenates them with object features in this encoding stage. And so let's go there first. So we use basically some description file of a robot hand that we typically have available, right, like a URDF file of the gripper, and then we generate the point cloud of the gripper in a given configuration, a joint configuration, and we use these point clouds as input to train an autoencoder to learn a low-dimensional latent space that encodes the geometry of the robotic hands in these specific joint configurations. And you see we use like a chamfer distance between these point clouds as a loss function here, basically. And so then we use the encoder to compute features in different hand configurations and concatenate them. So and specifically what we do here is we have a robot hand that is basically in different open or closed states, like at the very ends of the joint angles, at the very extremes and somewhere in the middle. Push them through this encoder that comes from this process over there, compute these features, concatenate them, do some weird arithmetic. We actually haven't ablated that part in the paper, which we should. Concatenate it, and then the output is a gripper feature. And so what is interesting about this is that we can actually interpolate in this hand feature space. And so this is a visualization of this embedding space. So we first compute, to create this visualization, what we've done is we first compute the features of two input point clouds. You see it's like one hand either closed or open, or like the fingers in a particular configuration versus in a different one. And here it's even two different hands, like in the bottom row. And so we interpolate between these two features and decode these interpolated features into a gripper point cloud. So this is what is happening here, right? So we just draw a line in the embedding space and then sample on this line, and then we construct the gripper. And what is interesting is that you can see in the top row, for example, the prismatic joint movement of this gripper, and the middle row. So this is the top row with the prismatic joint movement. The middle row shows the movement of this revolute joints of the fingers, and the bottom row really interpolates actually between the geometry of these two different hands, which is interesting, right? Like as an embedding space. And again, this is actually a 3-fingered hand versus a 2-fingered hand. Also something to note. So so we basically, to create the training data set for this autoencoder, we basically generated a bunch of very simple grippers, like these ones, and like a lot of augmented versions of this. And then we took real grippers, like this is the old Kinova gripper, this is like the Robotics 3-fingered hand, and all of this. We put all of these in there. And then actually tested also with unknown grippers that went in the training data set later. Yes?
So physically, what does interpolating between two grippers actually mean?
Yeah.
I like to work
Yeah, so I would say the first two rows are more clear, right? Like it's just line movement. And here it's like, it would be nice, right, like to rotate this point cloud and actually see what's going on. I don't know if there's just like a finger falling off in the middle. I don't actually know what exactly is happening. So I don't know, like I can see how the geometry maybe changes of the links. What exactly happens with that third finger in the process, I don't know, right?
Actually, my question is more, why was the input like two different fingers? What is the...
Oh, this was just, so this is more like to show that this embedding space makes sense and so intuitively makes some sense, empirically maybe, right? So it's not to somehow we didn't use this process of being able to interpolate in that way. It's more like at test time, when we have a new gripper that was not even seen, we can use this encoder from this previous slide. We can use this encoder up there and then even use this new hand in the point clouds that were generated from the URDF file to embed it or to get the feature out. And so it's somewhere in this embedding space. And if it's similar to the training hands, then hopefully like this feature makes sense and encodes the kinematics and geometry of that hand. Yeah, so this is not, so I agree, like we didn't really use this. It's more like showing that, okay, this space, this latent space actually has some useful information, hopefully in it, as visualized here. There was another question.
I had the same question.
You had the same question, okay.
I think the model is great. I just had a question about how you think this would translate to things like universal grippers, and whether there would be changes, a lot of changes.
Yeah, universal grippers, do you mean like the coffee grind gripper,
Exactly,
that one? Sorry, that's how I know. That's how I know. This is a very good question. So we didn't include grippers like this. And the reason why we didn't is because we actually picked specifically these contact points, which like one assumption that we make is maybe this is helpful, is that these contact points are specifically for precision grasp and fingers, while the universal gripper doesn't, I don't even know what it does. Like, it's not a power grasp, so it's definitely not a precision grasp like the universal gripper grasp. Like, it's like very different. You would parameterize it very different, not like with these contact points, actually. But I think just in principle, if you were to, so there are a lot of internal assumptions also on the data set that we use to actually train this model. So for example, we only have traditional hands in there with fingers. And for the labeling the data set, actually with successful grasp, we evaluate for closure and kinematic reachability, for example. So that's how we automatically label this data set that's used for training. And so that, I think, is more difficult to do automatically with a universal gripper. But if you could do it, in principle, you could include that in here as well. But yeah, I think overall, the assumptions are more like traditional gripper that you can parameterize by a set of contact points. Yeah. More questions? No. Okay. Okay, so I think maybe hopefully the gripper feature is clear now. And so let's move on to the object feature, which honestly is like kind of less interesting because it's just, I think we used a PointNet++, maybe with pre-trained weight. To be honest, I don't quite remember right now. But basically we use PointNet++ here, like, and it doesn't really matter honestly what the architecture there is. But then we concatenate these features and basically use a model that generates these contact points incrementally, conditioned always on either the first contact point or the second contact point. And so let's look at this model. It looks like this. It's very complicated, so let's skip over this. You can read about it in the paper, and let me just give you the intuition for what's going on, okay? Okay, so we are assuming we're having an n-fingered gripper, and the network has then n stages. And so in stage 1, the model estimates the probability for each point in the object point cloud if the point belongs to a valid set of contact points. And so after ranking these points according to this prediction, the model selects the top k points. So these are the top k points in that point cloud of this box object here, okay? Okay, so then condition on one of the points selected in this first stage, the model now predicts the probability of each point in the object point cloud to form a valid set of contact points together with this first point, okay? And then again, these points are ranked and the top k points are selected. So again, like these are the top k points given this is one of the contact points for this grasp. And then you can see where this is going, basically, and finally in step 3, we do the same thing. We select a third contact point from this point cloud, conditioned on the first two contact points, and then the network is basically trained to output that, again, what's the probability that these points together form like a good grasp, meaning it's in force closure and kinematically reachable. And actually, before executing the grasp, we still check kinematic feasibility for the hand, because there's no guarantee that it actually produces a kinematically feasible grasp. Questions on this?
It seems like you're just choosing the top point, so why?
Oh no, it's actually happening all in parallel. So this is just like kind of, let's like roll it out from this one point, but in actuality, it happens for all of these top k points.
And then at the end, whichever one is feasible.
Yeah, you take like the best one, the best set of contacts, and then you execute it and check this one.
And how do you determine the ordering of fingers?
How do you determine the ordering
of fingers?
Yeah, we don't care. We check basically post hoc. So once we have the set of contacts, then there's like a set of possible alignments, right? And then we check all of them for kinematic reachability. Yeah.
And then choose one.
Choose the one that basically works according to this check. Yeah. Yes.
How do you treat the proposal of the points?
How do you what?
How do you treat the model that proposes the
We basically have a labeled data set, right, that we generated in simulation where I forgot how many objects are in there, but we basically run this force closure. We generate random grasps. We check the force closure of these precision grasps and kinematic reachability and all of this. And then we have a supervised training setup, actually.
Yeah. For the graphs that you actually are able to generate with this method, are they tend to be similar graphs, or is there like a sort of variety of graphs that are learned naturally?
That's a good question. So you mean like if we look at all of these graphs that are seeded from this first stage, for example, how similar they are? That's a good question. I actually am not sure. I would say they are probably kind of varied because you could, right? Like you actually. Well, it depends also on the object, right? Like maybe, again, there are only very few precision grasps, especially not just power grasps, but precision grasps that actually work depending on the shape of the object. But in general, I would say there's nothing that prevents this method from generating actually very diverse grasps. But we haven't like formally looked at this. Yeah. Questions? Okay. Okay, so here are some examples of how this actually looks like. So this is just a toy example to visualize how the model predicts reasonable contact points that are dependent on the gripper geometry. So in black, what you see is the object, and in blue you see the gripper in two different configurations. And so these are actually at the joint limits, right? This is fully closed, this is fully opened for this particular gripper, just for making an example. So, so this first gripper has a very small opening, and so this model actually has to generate grasp only at the thin part, right? Because it can't grasp it, for example, at the sticker part over there because the gripper cannot open further. And so the second hand that can actually fully open like this, but can only close to this extent, the model actually predicts at this larger area, the grasp, and not here because it couldn't probably fully close to actually get a good grip on this object. And here is a third one with a 3-fingered grasp, just to show that it can also generate feasible, or on the same object it can also generate like feasible 3-fingered grasp, for example. Yeah.
Actually, I have a question on the previous slide. That how do you down select the points, contact points, like what criteria are used to actually score them with, like which is good, which is not good? So
yeah. So what we have in our data set is labels for the grasp that say it is in forced closure, so like a stable grasp, and it is kinematically reachable as well. And so, so this is the label that we use to train this model that actually predicts a probability for each contact point to be part of a feasible and forced closure grasp, essentially. So that's what we do inside of this complicated model that I flashed at you, basically.
How do you check the feasibility of generated grasp proposals?
How do I check the feasibility of the generated grasp proposals?
Yeah.
So basically I have my hand, I know exactly the geometry, right? That's how I created this input to this model. And so I can just run like an inverse kinematic solver, for example, to align the fingertips and all of these different permutations of alignment between fingertips and contact points to see if they are reachable without collision. Either self-collision or collision with the object. Does that make sense?
Yeah.
Okay.
Do you think if you have a model which can predict the center of gravity of an object, and I mean, if you have that model available with you, will that in any way can help you in improving this, or maybe like speeding up the or down selection or whatever,
Yeah, that's interesting. So in the data set, of course, we need to know for each object the ground truth center of mass to actually check force closure, for example. That's required to compute force closure. And so therefore, I would say we haven't explicitly included this in the model because at least it's kind of baked into the data set and then the labels there. But you could potentially, we haven't tried this, but you could potentially estimate explicitly the center of mass, actually from the data that we have, and maybe provide this as an additional input, potentially. We haven't tried this, but it could potentially improve results. Okay. All right. So we already went through this. And of course, we have lots of real-world robot data on all of these different objects. And again, this is precision graphs, right? Like, so these are graphs where there are much fewer possible graphs that are actually in force closure or not. And we've done tests with all of these different hands. One thing that is kind of funny is we created a two-fingered hand by just giving the model a hand where we removed in the URDF file basically just one finger, so that we had like at this point when we did this work, we didn't have other two-fingered grippers. So that's what we did here to create an unknown robot arm. But here's, first of all, some examples of grasping novel objects with a known robotic three-fingered hand. And we get from these 65 trials on these novel objects that the model hasn't seen before, a very high success rate. But I think the most interesting experiment is actually this one, where we wanted to know if we can grasp novel objects also with novel grippers that were not at all in this data set. So here are some examples. Again, this is like this funny one where we basically pretended it was a two-fingered gripper and generated two contact points for two fingers. Here's one with the Allegro hand, where again we had a baseline. I'm sorry, but I actually forgot what the baseline was we used here, but clearly it wasn't doing very well. Maybe we tried to generate contact points, sample just contact points. I'm not sure anymore. I would need to look this up. But we are getting a pretty high success rate. And again, like this, these are actually fairly small objects that have to be grasped with this precision grasps. And here are also some failure cases that are, for example, due to imprecise perception, there's a lot of noise on the point clouds, especially for these kind of thin objects that you see here, or it's low friction, premature contact, let me play this again, or just object deformation as well. Also, you see this thumb was kind of hurt, it has a band-aid, if you look at this again. This was this model that we have done. So it's called, if you're interested in all the details, please check out this paper. And again, the main idea was, given an object in a hand description, you can compute contact points. And the algorithmic contribution was this particular network architecture that we created. And the result was this model that outputs valid graphs also for novel hands, not just for novel objects. Yeah, and with that, I'm at 9. Sorry, I'm not at 9 p.m. I'm at, sorry, this is like, it's going to be Pacific time, but this is noon. So I have like more works. I even have a hidden work that I'm definitely not going to talk about. Maybe I can super fast like breeze over this second work, or maybe just to recap for this work. So the reason why I showed you this is because I think in this Oxy data set, you could do much more if you actually condition the policy also on the embodiment, for example. And one way on how to do that is what I showed you. You could actually, take the URDF file of these robots, right? Create this point cloud and maybe create this latent representation over all of these different robots that are in this data set and then condition on it. So I think this would be like a cool idea that I'm trying to convince my students to work on, but maybe one of you works on it. Anyway, so that's the reason why I showed you this very grasping specific work, but I think some ideas can transfer as well. And so the second work, just to breeze over it, here the idea was to basically avoid the correspondence problem. So in this UniGrasp work, we actually said, okay, the contact points are the ones that are the same over all of these different hands that are have all fingers, right? But for example, for this universal gripper, right, like that wouldn't work. But what if you don't try to solve this very hard correspondence problems between these different embodiments, then maybe you would do better at actually including these kinds of non-traditional hands, for example. And so the insight that we had in this work is that it doesn't really matter how the door is open, it only matters that it is opened. And that's what you want to learn. That's what you could, for example, capture in a reward function that encodes a notion of task progress and thereby is invariant to the embodiment performing the task as well. And so that's the main idea of this work, where we basically take a lot of data of robots, toy robots in this case, that are doing the same task, but because of their embodiment, they're doing it in completely different ways, completely different strategies. And we learned a embedding space with the temporal consistency loss that thereby, because of this loss, encodes this notion of task progress. And then we can use it as a reward function where if we take for an entirely new robot, so this guy over here, for example, we can use this embedding or this encoder that we learned in this way, get the current embedding in that space, compared with the goal embedding, compute the L2 distance between them, and then we get a dense reward for our reinforcement learning method. And since I'm totally out of time, I'm just gonna leave you with this general idea and maybe show you some cool, maybe not, there's not enough time. But anyway, it works actually really well. And it doesn't just work with these funny stick figures, it also works with, at this point, right, like we had like some human data sets as well that we then transferred to a robot as well, or we also built our own data set with all of these funny toys and tried to basically transfer between these. So here you have this data set, and then if you learn a reward model on this, this is not playing. This also has some videos which are for some reason not playing. Interesting. Anyway, there's basically, although you learn on these person, like using all these tools to put the pens into this container, the reward function actually does the right thing when you embed these images into the space as well, and gives you an idea of how far away you are potentially from a success. Okay, so let me close with this. So I think this is actually also potentially a great idea to revisit, where we basically learn an embodiment invariant reward function that encodes task progress. And it's self-supervised using this self-supervised loss of temporal cycle consistency, where you don't need labeled correspondences, which was the thing you actually needed in that UniGrasp paper. And then you have a very simple reward formulation that allows you to learn policies in a sample-efficient way. I have also some work where we embed structure into policies, which I think is always another good way on how to reduce data hungriness of current algorithms. So here we embedded actually equivariance into a policy structure. And this will be presented at XIRL. If you're there, happy to talk about this as well. But I'm going to jump over this and kind of close the talk. These were the 4 works that I wanted to talk about but didn't. And that hopefully, first of all, motivated why learning a cross-embodiment could be really promising for getting more data in robotics, which we need. And here's some ideas on how to do cool things with this data set. With that, I'm looking forward to talk with you all during the rest of the day. Thank you very much.
Maybe we can take a question or two from the audience. I can ask a question. So I guess you mentioned like one of the dreams is to learn from this YouTube data, human videos, 3D, or the third person rather. I guess what are the gaps there?
The first one is of course that different from these robot data sets, for a video of a human doing something, you don't have the joint angles, you don't have the pose of the hand, you have to do all this post-processing. And so with current methods that actually do detect hands in images or videos, they're still extremely noisy. And they typically don't work when you have like occlusions, which is what is exactly happening during manipulation, right? So I think that's one of the challenges. But I think people have used these data sets, like let's say Ego4D or Epic Kitchens, to at least pre-train a representation so that when you use an image of a robot, you can maybe use the same representation to embed it. So that's one way on, again, like how to not exactly make this correspondence. Another one is to learn from the human data sets. You can learn also a reward function. So one thing we have done in the work that I haven't talked about, it's called Concept to Robot. There we trained an activity classifier that is trained actually on human data sets and says like, oh, this was like someone opening something, or this was someone closing something, throwing something, whatever. And then, because it was a video activity classifier, we could also execute that same classifier on a robot video, and thereby tell the robot like, oh, this did not look like you closed actually something, which is what I want you to do. And that also helped in learning policy actually as well. So that's maybe another idea on how you could use human videos without trying to do this explicit correspondence. Yeah.
So the last question. Sorry.
I was thinking about the fact, sort of related to Ani's question, that when we make videos on YouTube, we rarely focus on our hands. And so all that data is not there. But there are activities that are hand-specific. The ones that are coming to mind, maybe they're like a terrible idea for grippers right now, but the first one I thought was crochet, which probably maybe is a little too hard, but at least all beginner videos in that will always focus really closely on what the hands are doing.
Yeah.
The other one I was thinking was henna. So actually like making designs on a hand, and you might actually, in those cases, the videos might actually be taken in a way specifically to show how to use your hands. But most YouTube videos are not about how to use your hands.
Yeah. I totally agree. It's like in the crafting space, basically, you have all of this, right?
Yeah.
And then actually Ego4D, you know, what they did is like they basically gave a bunch of random people this headset that they had to wear, I don't know, like a specific amount of time during the day. And apparently they have a lot of crafting videos. So a lot of stuff about deformable objects and crafting, because that was kind of, I guess, like the least awkward way to wear this thing, right? Like you're not, otherwise you have to go out and get into the world anyway. It doesn't make sense. So a lot of people like did stuff at home and did actually hours and hours of crafting. So there are a lot of hands in there. Okay, so let's say, or soldering. Yeah, I think there are a lot of them out there. But the thing also with this is that none of the things that are in Ego4D, or very few of the things that are in the Ego4D datasets, for example, are actually in the current capabilities of robots. And like this is because of hardware, but also just controlling them, or like it's just very hard to do these things. Like that's, I think, what you were getting at.
I was like, that's out. But
maybe it was like these huge needles, right? There are these people who.
I was thinking it was something where either you have a tube or you have like one end effector, but it's still pretty.
Like even with crocheting, it's like you need this coordination of two as well. It's like insane. The other thing is like, okay, let's say you don't have all these videos with the hands in there, then maybe you can do this more task-specific reward thing that I talked about. Very like kind of went really fast over it, but that could maybe be a way to get rid of that challenge, or sorry, not to get rid of it, but to deal with it in some way. Yeah.
All right, so let's, I was going to say, I guess we're a bit over, I think, 12:15. So if you have more questions, feel free to stop by Robotics Social and we're going to